Morning, everyone. Here we have Srinivasan Arunachalam talking on some problems in quantum state learning and testing.
Hey, thanks everyone for coming for the first talk. Thank the organizers for having me here. I think there are many people here whom I've read a lot about, like the Matami survey, and I've learned a lot about the survey, what I'd like to make towards the video, and there are many people here I would have loved to meet, and it's very nice to be here. So today I'll be talking a little bit about quantum. I guess there are not too many people here who are very familiar with quantum, so I hope to keep it slightly light. But I wasn't aware of that before I prepared it, so I just did an all-nighter and I kind of made the slides a little bit more classical friendly. So hopefully you get something out of it. I'll be surveying a few results that I've had in the past couple of years and things I've been interested in recently. So let me jump right into it. So I'm not going to give too much motivation to why I care about these problems, because I think the workshop is about testing and learning. So property testing and learning theory, these have been fundamental questions in theoretical computer science. People have been studying this in classical TCS for the past 30 years. There have been applications to communication complexity, information theory, property test, many more than that. And so let me just tell you what the problem is in classical property testing. So you just have a script P, that's just a collection of n-bit Boolean functions. Somebody comes up to you and gives you query access to a function G. So G is just an n-bit Boolean function, you don't know anything about it, but you can make queries to it. That is, you feed it X and it tells you G of X. And your goal is to decide if G lies in the property or the distance between G and the property is far. So either this function G lies in this class script P, or G is far from every single element in script P. So if you look at the truth table distance between G and every single element F that lies in script P, the difference is at least epsilon, or they agree on at most 1 minus epsilon. And you promise one of these two is the case, and the goal is making queries to it, decide which is the case. And as always, the complexity measure that, at least for the rest of this talk, I'll be carrying over is query complexity, the number of queries that are necessary and sufficient to decide which of this is the case, given query access to the unknown function G. So this is classical property testing. And then, this is, I think, for the past 35 or 40 years, we have looked a lot at classical property testing, and I think the first seminal work of Bloom, Rubenfeld, and Lubin, they showed the linear functions can be tested with just 3 queries. And this was the basis for the PCP theorem. People started building upon this and realized that maybe you can actually just with constant many queries test any property. And the linearity testing was the start of this.
I'm sorry, why it's less than 1 minus epsilon?
The point is I'm just promising you that G is far from every single element in it.
But it's not far. Well, I mean, maybe it's 0.001, it's still less than 1 minus epsilon.
Right. So the point is the query complexity would depend on epsilon as well.
Okay.
Yeah, so I'm allowing the query complexity to depend on epsilon. So for now, I'm just being hand wavy. You can think of epsilon to be a constant at most exactly 1 or at most 0.99.
Right. So the distance is at most 1, so we call 0.05 far. It's the nomenclature.
Right. But the query complexity would depend on epsilon. So if epsilon is super tiny, like what you're saying, then the complexity can blow. We're totally fine with that. So what is quantum property testing? You just replace all Boolean functions with quantum states. That's it. So script P again is just a collection of n-bit. Sorry, there should be no functions here. It's just n-qubit quantum states. And now somebody comes and gives you and hands over copies of an unknown quantum state psi. And your goal is to decide if the unknown quantum state psi lies in this concept class or the distance is far. So this is just the inner product between 2 quantum states. I'm going to have a 1-slide primer on what quantum states are in the next slide. But for now, you can just think of replacing all Boolean functions with quantum states and everything just stays the same. Here you have query access to this unknown function G. Here you have copies of this unknown quantum state psi. And the goal is how many copies, again, are necessary and sufficient to distinguish whether psi lies in the property or psi is far from every single quantum state in the property. Quantumly, I think property testing has been fairly slowly growing. I think it's much more nascent than classical property testing, but there have already been very good results in this field, which have for example, QMA2 equals to QMAK, requires testing productness and so on. That's a fundamental result. But I still think there are many more interesting questions that are open, and I think they are just hard to tackle because of mathematical tools. And the the main motivating question for this talk is what classes of states can we test and learn efficiently? Right. So yeah, let me just give you a one-slide primer on what quantum computing is. I'm not going to say too much. I'm just going to tell you what might be just sufficient for this talk. Yeah, please feel free to stop me at any point. So classically, a bit is 0, 1. So like you just have an n-bit string, so each bit is either 0 or 1. That's it. Quantumly, instead of classical bits, you have qubits or a quantum bit. And you can think of a qubit as just lying as an element lying in C2. So it's a two-dimensional vector. And it has a basis, like how classical bits are 0 or 1. Quantumly, I'm just going to put this is called ket, and this is called, so this ket 0 and ket 1. These are just like computational basis elements, 1, 0 or 0, 1. So this is a basis for C2. So every quantum state, every qubit can be written as 0 and 1. In terms of 0 and 1. But of course, the question is like, if these were the only two quantum states that were possible, that's just classical. Like, there's nothing more going on. So is there anything more to it? And the answer is yes. There are infinite possibilities, and that's the idea of superposition. So what is superposition? Superposition says a qubit can be not just 0 or 1, like a classical bit, but it can be 0 and 1 in some sense. And the and corresponds to the fact that 0 and 1 come with some amplitude associated to it. So think of this unit vector alpha and b, which has alpha on the first coordinate, beta on the second coordinate. I'm forcing the fact that it's a unit vector, so alpha squared plus beta squared is 1. So this is a superposition. So this is a valid quantum state. So any C2 vector whose L2 norm is equal to 1, that is a valid quantum state. And you can always decompose this as follows. Let's just look at an example maybe. So maybe this is a quantum state because like 1 over 6 plus 5 over 6 is 1. So it's a valid quantum state. And you can always decompose it in terms of ket 0, that's the computational basis, times this amplitude 1 over root 6, ket 1 times this amplitude I times square root 5 over 6. So this is a qubit and this is a valid qubit. So this is what I mean with superposition. So this is a valid qubit, whereas classically it could have just been 0 or 1. Right, so is this the only possible quantum state? No, you could have like more qubits. And I'm not going to talk of entanglement and things like that. All I'm going to say is a quantum state, a k-qubit quantum state, is just an L2 1, a vector in dimension 2 to the k, whose L2 norm is equal to 1. That's it you need to know. So one qubit is in C2, k qubits in C2 to the k, and you can just like, you can think of it as a giant vector on C2 to the k. As long as the sum of the amplitudes is equal to 1, that's a valid quantum state. So it's just an L2 norm 1 vector, that's it. What's a valid operation on a quantum computer? Again, I'm not going to go too much into this, but you can just think of any unitary matrix that you apply onto my quantum state, my vector which has L2 norm 1, that's a valid operation on a quantum computer. So that's all there is. So yeah, so far I've spoken about superposition, k-qubit quantum state, what's a valid operation. The next natural question is how do I get information out of this quantum state? And that's called measurement. The measurement mostly I'll be talking about in this talk is just computational basis measurements. So if I give you this quantum state, this is a valid quantum state. If I measure this, I will get 0 with the square of the amplitudes. In this case, it's 1 over 6. So I get 0 with probability 1 over 6, 1 with probability 5 over 6. So given any quantum state, I just choose to measure it. I will get x with probability alpha x squared. So here k was 1, so in this case it's 1 over 6, in this case it's 5 over 6. And the annoying thing about measurement, but that's quantum mechanics, is once you choose to measure, you will lose the unknown quantum state psi. So you have a quantum state, you choose to measure, you're going to get a classical output out. You can do whatever you want with it, but you lost the unknown quantum state that you chose to measure. Yeah, so like every quantum algorithm, every quantum algorithm just starts with an unknown k-qubit quantum state. Think of it as a unit vector in C2 to the k. You apply a bunch of unitary matrices, and you get another quantum state out, and you just choose to measure. And the hope is that with this simple two-line process, you hope to solve something easily with a quantum computer, but not with a classical computer.
What is lost?
The point is this, the quantum state is lost. You cannot choose to measure it again. So after you do this measurement, you will just collapse to this computational basis state. You won't have this nice superposition anymore.
So you get these two numbers instead of the state.
You will get only one number. So for example, so the thing is like it's randomized in the sense. If I choose to measure this, I will get 0 with probability 1 over 6, 1 with probability 5 over 6.
Ah, I see.
So let's just say you got 0. Yeah, sure. You didn't learn the fact that there was a 1 with amplitude 5 over 6 in there.
I see.
Yeah, so I think, long story short, like quantum computing is just a fancy way to play with linear algebra. You start with unit vectors, you apply unitary matrices that are still unit vectors, you just choose to measure, and that's it. There's nothing more to it, and hopefully I'll just talk about, these are the basic concepts that you need for the rest of my talk. Okay, good. So let me tell you what I'm going to be talking about in the next, for the next 1.5 hours. I'll be looking at very simple quantum states, and I'll be talking about testing and learning these simple quantum states, and surprisingly, even these simple quantum states, we didn't know how to test and learn them like in all parameters and regimes. So the first thing is stabilizer states. You don't need to know too much about Clifford circuits. I'm not going to talk too much about them, but this is a very interesting class of circuits. If you just look at a Clifford circuit, it just consists of a bunch of gates. If I apply the Clifford circuit on the all zero input, the output is called a stabilizer state. And the reason why Clifford circuits are interesting is because it's known to be classically simulable and easily implementable. So if you ask somebody who has a quantum computer to run a Clifford circuit, they should be able to run this Clifford circuit pretty well enough. Right. Okay, maybe this is too much quantum for you. Let me just tell you what a stabilizer state even looks like. It's very simple, actually. So this is my valid quantum state. So to define a stabilizer state, you need 3 things. You need a affine subspace in 0, 1 to the n. You need a matrix, n by n matrix, and you need a vector S. So these 3 things define completely a stabilizer state. And how's the state defined? It is just a superposition over all elements in this affine subspace with amplitudes. That is I to the S transpose X, that's the inner product between this n-bit vector S and n-bit string X, and X transpose Mx. That's just a degree 2 function in X. And the amplitudes are 1 over square root of A. You can kind of quickly verify this is a valid quantum state because the amplitudes of this is just 1, so it's 1 over A, and there are A many things in the summation, so it's a valid quantum state. So this is a valid quantum state, and I'm claiming to you this is interesting because these are things that people in quantum have looked a lot at.
Is this if and only if, or is this
yeah, I think so. Yeah.
This is a description of Clifford.
Mm-hmm.
So if you give me such a state, I can give you a Clifford also that prepares the state.
And there's another way to think about Clifford circuits, which is that they're unitaries that stabilize Pauli's.
Yes, I will come to the formalism bit. Yes, exactly. But for the purpose of this talk, this is a family of quantum states that I would like to test and learn in this for the first part of my talk. Yes.
Sorry, up in the first one, then output of psi is equal to C. So what kind of object is the C?
So it's a Clifford circuit. There's for example, how classical circuits have and or not gates, and or NAND gates. Like Clifford circuits have a basis called the Hadamard and the phase gate and things like that.
So the C is an operator on the right.
Yeah, it's a unitary.
Exactly, it's a unitary matrix. The unitary matrix consists of 3 gates in them.
So basically, this tells you that's the definition that you look at the C. Or is there any deeper meaning in that psi is equal to C equal to 0 instead of maybe 1 or something?
Oh, so the point is, there's no deeper thing than that. I think I know what you're trying to say, but I don't want to go more than that. I think for the purpose of this talk, just think of stabilizer states as just states of this form. They are prepared by interesting class of circuits, and we would like to learn and test these states. Maybe offline I can tell you why C times 1 to the n was also interesting, but for the purpose of this talk, that's not important. Good. And the second class of states that I'll be talking for the next 45 minutes is degree D phase states. So this is a class simpler than this. At least this had complex numbers. I'm saying I don't like complex numbers. So just think of a uniform superposition over all f2 to the n. And the phase is just -1 to the f of x, where f is a degree D function. So it's just exactly this, except the fact that a is just 0, 1 to the n, and s is 0, and this is just a degree. Here it was degree 2 for stabilizer states, but I can think of degree D functions, where d is arbitrary. So for the first part, I'll be talking about learning, testing, and tolerant testing stabilizer states. So the first 2 things are well known in literature. The third thing is something we had recently. And for the second part, I'll be talking about learning degree D phase states and testing degree 2 phase states. Testing degree 2 phase states, that's something I think that was unknown.
Degree here is Fourier degree or is F2 degree?
F2 degree. Yeah. So both these results are, the first one is going to be slightly quantum-y, but I think the proofs is heavily inspired. So this is seminal work of Sarmanitsky who showed about the inverse Gowers norm. We in some sense quantize the proof and get the first result for tolerant testing stabilizer states. So the half of my first talk will be devoted to proving that. And the second thing is going to be a lot about looking at evaluations of polynomials on bit strings and understanding how low degree polynomials agree or disagree. So they're going to be quantum-y, TCSE, mathematical, but I hope to put everything together here. Yeah, so let me talk about learning quantum stabilizer states. So to begin with, so to understand stabilizer states, first you need to look at what are polymatrices. So polymatrices are just a basis for all 2 by 2 matrices. So there are 4 polymatrices: identity, X, Y, and Z. So this is just the identity matrix, X just does something, Y has a complex phase in it, and Z is just like a phase rotation. And these are all orthogonal with respect to the trace inner product, and they form a basis for the 2 by 2 matrices. You can also look at an n-fold tensor product of these matrices. What I mean by n-fold tensor product, you can mean X tensor Y tensor Z, X tensor identity, and so on and so forth. So an n-qubit poly is just, you pick an arbitrary one of these 4 things, take an n-fold tensor product, and this is again orthogonal with respect to the trace inner product, and they form an orthonormal basis for the set of n by n matrices, where n here is 2 to, capital N is 2 to the little n. So there are 4 to the n many polys because there are 4 here, and I'm taking a little n product, tensor product of it. There are 4 to the n polys. So you can kind of associate every single poly with just a bit string even. You can think of every poly as just associated with a 2n bit string. So if you just want to do mathematical comparison, there are 2 to the 2n many things here and the 4 to the n many things here. So there should be some sort of bijection between the polys and the set of bit strings. So that's fine. But because we're kind of talking about matrices here and not just arbitrary n bit strings, you can view every poly as a bit string, but the inner product is slightly different. So there's something called the symplectic inner product. So the symplectic inner product is if I give you x and y, the standard inner product just does x1, y1 plus x2, y2 plus x3, y3 up to x2n, y2n. That's the standard inner product. But the symplectic inner product, so what it does is it looks at the first n bits of x. We call x as a 2n bit string. Looks at the first n bits of x, takes the inner product with the second n bits of y, looks at the second n bits of x, takes the inner product with the first n bits of y. This might be slightly mysterious why this is the case, but kind of this inner product takes into account the fact that implicitly we're talking about matrices here. Because when I look at the inner product between x and y, for example, because they are phases and the matrices, they do not commute with one another. Because they do not commute with one another, I need to take into account the fact that they do not commute in this inner product, and the symplectic inner product seems to be the right definition for me to define how the inner products between these matrices work. I'll come back to this again later in my talk. Right, so if you look at the 4 to the n many polys that I formed here, I'm going to call them Wx. These are called the Y operators. The 4 to the n many polys, they form an orthonormal basis for n by n matrices. In particular, I can write every quantum state in terms of this decomposition. So let me first say what I mean by that. So think of a quantum state psi. So I've not defined this notation, but I told you ket psi was just a big unit vector. Take the unit vector times the broad version of it. So that's n by 1 cross 1 by n matrix. So that's an n by n matrix. So this notation is just like this times the conjugate transpose of it. And every quantum state can be written in terms of the poly decomposition this way. Because it's an orthonormal basis, I can rewrite every quantum state this way. And these coefficients are just like the standard coefficients that you would expect it to be. And because these things are orthonormal and have trace inner product 0, it's not too hard to verify that the sum of squares of this alpha x squared is equal to 1. Yeah, you can take this for granted, but I mean it's an exercise if you just go back and sit down and write it out. Yeah, so for the rest of this talk, I'll be kind of talking about an analogy between why this representation is going to be useful for us. And the reason is there's this distribution called a characteristic distribution. That's just alpha x squared divided by 2 to the n.
1 second. Why you have so many Wx, but in the formula you have much less Wx? You have f
Oh.
2n.
Oh, sorry, this is a typo, this should be 2n, sorry, you're right, sorry, that's right, sorry. Right, so the characteristic distribution p psi is just alpha x squared divided by 2 to the n. So the nice thing about defining the characteristic distribution this way is because it's actually just a probability distribution. And maybe if this is again a little bit too much quantum for you, like maybe you can draw inspiration from classical literature. Like we know that every Boolean function, where it maps n bits to -1 bits, has this nice Fourier decomposition this way. So chi-s are just like character functions that form an orthonormal basis of just vectors. You can think of polys as just a characteristic basis that form the basis for matrices. And you can think of p psi of x as playing the role of f hat of s. And if you know that this is -1, 1, we know that this is 1 by Parseval's theorem. Sum of squares of this is equal to 1 by Parseval's theorem. So this, if you forget the renormalization, so kind of like summation over x, alpha x squared is equal to 1. So kind of like drawing inspiration from standard Boolean function analysis, like how you can express every Boolean function in terms of characters, you can express every quantum state in terms of the while operators. And the coefficients are kind of what I'll be looking at. Good. So I think that's all I need. That's all I need to start talking about learning stabilizer states and testing them. Okay. So, right. So as I said, what's a stabilizer state? It's the output of a Clifford circuit. It's not super important what the Clifford circuit is, but we know this at least it's an interesting class of states for quantum computing. So like what Joe was mentioning, there's an alternate way to write a stabilizer state. You can define every stabilizer state as just the set of, it's just defined by a stabilizer group. What's a stabilizer group? Let me just tell you what that is. So there are 4 to the n many polys here because there are 4 polys and I'm taking the n-fold tensor product. There are 4 to the n many polys. Let's just say I pick a 2 to the n maximally commuting group within the set of 4 to the n many polys. And I look at a state that is an eigenone state of all these polys. So a stabilizer group is just a subset of all possible while operators such that psi is stabilized or is a +1 eigenvector of all the polys in my subgroup or my stabilizer group. So, and I'm not giving you a proof why this is an alternate definition of this, like why does the first line and the second line, why are they equivalent, but you can assume it for now. Every stabilizer state is completely defined by a commuting subgroup of all the while operators, where the commuting subgroup has size 2 to the n and it's maximally commuting. Yeah, this is something you can assume for now. So recall, like I said, like the poly matrices form a basis for all n by n matrices, and every quantum state phi can be written in terms of this way, and I define this characteristic distribution this way. So this is something I discussed in the previous slide. So classically, when you try to do learning or testing, one thing you often do is something called Fourier sampling. You sample from the distribution of the squared Fourier coefficients. Like that's what Goldreich-Levin gives you access to. So quantumly, there's something called Bell sampling. So you would like access, for given an unknown quantum state phi, I would like access to this distribution p phi of x. And that's exactly what Bell sampling does. I'm not going to describe the procedure exactly, it's a very simple procedure, but it involves a little too much quantum, so I'm not going to go into that, but just take it for granted. It takes 2 copies of my unknown quantum state psi, and it produces a sample z from this distribution p psi. We know p psi is an distribution, and you can get a z that's sampled from this distribution p psi. So for every quantum state, I could have just done this. So there is a quantum way to describe this, and there's a totally mathematical way to describe this of just taking derivatives. I'll be talking about that in the next part of the talk, but for now I'll not talk about it. So psi is a stabilizer state. Then we know that there are only 2 to the n many polys in the stabilizer group that stabilize the state. So in particular, if you just write this expression out, what is p psi of z? Is just this expression by definition. We know that if WZ stabilized psi, WZ times psi was exactly psi, because it's a +1 eigenvector, and psi inner product psi was just 1, so it's 2 to the minus n. So we know I gave it 2 to the n many polys, and each one had exactly value 2 to the minus n, so these are the only non-zero expectation values in this wild distribution. So there are 4 to the n possibilities in this wild distribution, but I told you exactly the non-zero ones in them. Those are exactly ones which are stabilized by my unknown quantum state. So in some sense, what does Bell sampling do for me? It gives me one basis element for this group. So I do Bell sampling, I get a z, and I know that z was a basis for this group. Now the learning procedure is pretty simple. I just repeat this n times, I get a basis for this entire subgroup of size little n, repeated n log n times say, I get a basis for this group, it's of size n, and I just take the span of m, that's my stabilizer subgroup. And once I learn my stabilizer subgroup, that completely characterizes my unknown stabilizer state. And the sample complexity is little n. What does it get over?
We started at 9:50 or so.
9:50, okay, so 20 minutes, okay.
But take your time. There's 10 minutes between the break.
Okay, sure. Right, so maybe if this was again too much quantum for you, just think of like Bell sampling as a procedure that helps you sample from this distribution. With a little bit of analysis, I told you that this distribution is actually interesting because it produces me a basis for the subgroup that characterizes my unknown quantum state. So give me one linearly, so if I just obtain n many linearly independent Pauli matrices, this characterizes my unknown quantum state. So this is learning, it's pretty simple, and this has been known for quite a long time. So you can also talk of testing. I'm just recalling the definition from my previous slide. So again, this was just Bell sampling again. So there's something you can do about testing. Like the question is like, if I give you copies of an unknown quantum state psi, tell me if it was a stabilizer state or far from a stabilizer state. How would you do it? The previous slide told you how to learn the stabilizer state, but I just want to test it. Do I still need n copies or can I do it with fewer copies? So this was unknown for a very long time, but only like 3-4 years back, this was completely resolved. Given that I told you stabilizer states have been studied so well in quantum, like we didn't know how to test them even efficiently, like until just like a few years back. And the protocol is actually pretty simple. So the idea is you do Bell sampling twice. So you take 4 copies, you get a Z1 from this distribution, Z2 from this distribution, and you use 2 more copies and you just estimate this. And forget the renormalization, just estimate this. And I've not told you how to estimate it, but let's say you can estimate it efficiently with just 2 more copies. And if it's close to 1, you accept, otherwise you just reject. Right, so totally it just takes like 6 copies, and the surprising thing is if you look at what's the probability of this test accepting, let's just look at the left-hand side here. So this was just like, I got a Z1 and Z2 from this distribution P psi, evaluate P psi of Z1 plus Z2. That was my estimator. If you write this out, that's exactly this. And if you write the Fourier decomposition of all these things out, that's exactly this. And surprisingly, Gross, Nizami, and Walter in 2020, they show that if this quantity is at most 1 minus epsilon, then psi is far from stabilizer states. And if you're familiar with classical Boolean function analysis, this is remarkably similar to the BLR analysis. Like for checking linearity, I just query my function on x, y, and x plus y. If they agree, I accept. If they don't agree, I reject. And this is remarkably the same analysis there. There they use 3 queries, but here I use 6 queries because to get 1 sample, I had to take 2 copies from this Bell sampling procedure. Again, I'm not going to go to the proof of this. This is a 1-page or 2-page proof, but surprisingly, it's very similar and it's very inspired by the BLR analysis. Right, so I think so far I've told you kind of how to learn stabilizer states with n copies, how to test stabilizer states with just 6 copies. And the next part of the talk is about tolerant testing them. Do you have any questions?
Sorry, so this stability testing, is it actually related somehow to linearity? Like,
It is. So in some sense, it's actually the first slide. So if you look at what stabilizes a non-quantum state, it's just a subgroup. So if you think of a subgroup, if Wx stabilizes my state, Wy stabilizes my state, Wx times Wy should stabilize my state. Wx times Wy is just W of x plus y, so that's why you just check it. So essentially it is linearity testing under the hood. But yeah, the fact that this wasn't explored for a very long time was actually very surprising. Good. Let me talk of tolerant testing. Yeah, so also this is some joint work with Arco Paul, which appeared like a few weeks back on Archive. So let's look at the following thing. I give you copies of an unknown quantum state psi, and the goal is psi close to a stabilizer state or far from a stabilizer state? Is the inner product or the metric of how close they are, is it at least epsilon 1 or at most epsilon 2? So this is tolerant testing, and can we decide which is the case? I'm not going to go into too much motivation about this. I think like Shivam spoke a fair bit about this yesterday. Let's just say you can run a Clifford circuit on your lab. Of course, it's going to be slightly noisy. You cannot exactly prepare it. You're going to prepare something that's close to stabilizer or far from stabilizer. Can you kind of test whether you did a good job? And kind of tolerant testing, there's this long line of research even classically on why you can tolerant test some quadratic functions, linear functions, and it has implications to MIP and PCPs. So potentially this could be useful in more complexity theory, quantum complexity theory. So this previous work that I mentioned, Gross, Nizami, and Walter, they require the fact that you have to be a stabilizer state or far from stabilizer state. So they used 6 copies, and they worked only when epsilon 1 was equal to 1. There was a follow-up work of Grewal et al., where they reanalyzed this Gross, Nizami, and Walter, and this got this epsilon 1 to 0.79. But these two things are not tolerant by definition, because you require this assumption that epsilon 1 is 1, or epsilon 1 is at least some constant, and the epsilon 2 had to be accordingly picked. But they still got like sample complexity constant, like this was 6, and I think this also was 6. And the time complexity is always n. And the main question that I'm going to be answering in the next 15 minutes, I guess, is like, what about arbitrary epsilon 1s and epsilon 2s? So like, what if epsilon 1 is, say, 1 over log n or 1 over root n, and epsilon 2 is arbitrary? So this is called the low error regime. And in this setting, the question is like, can you still tolerantly test them? So for a long time, we were not sure whether this was possible or not, because we do have hardness results for learning approximate stabilizer states. If you slightly add like 1 t-gate to a stabilizer state, this is known to be as hard as learning parities with noise. So it's not clear whether this was possible or not, but kind of like using results that are very inspired by classical TCS, one thing that we were able to show is you can get a constant. What I mean by constant is n independent, constant sample and polynomial time algorithm for tolerant testing stabilizer states.
Could you speak about like the intuition for why tolerant testing should be harder than normal testing?
The point is, when you're given copies of an unknown, for example, at least if you look at Gross, Nizami, and Walter, when you do this analysis, this BLR type of analysis, you know the fact that when you look at summation p psi hat of S full cube, when I know it's a stabilizer state, I exactly know what the quantity is. But if I know it's only close to stabilizer state, I don't know how the characteristic distribution is going to behave. The characteristic distribution could not at all be a good proxy for how close you are to my stabilizer state or not. So the point is, if you're close, I need an estimator that, if large, would mean that you're close to stabilizer state. We don't have such a, they could, like both the estimators that GNW and Grewal et al. GIKL looked at, they were not tolerant in some sense. They only work when you are a stabilizer state. Or you have to be super close to a stabilizer state for the estimator to be a good proxy. But if you're much further away, say 1 over root n close to stabilizer, which is still close, but not that close as you would expect, we don't have any estimators for how close you are to a stabilizer state.
I see. So even like classically for linearity testing, the idea is like this estimator is not like Lipschitz with respect to the distance from the set.
Classically, we do know something. Maybe I'll come to that in a couple of slides. Like, because like the proof of this is heavily, like we just take a classical proof and kind of quantize it. Like you can call it that way. Although there's a lot of hurdles to do that, but kind of like, so classically we know how to do tolerantly test these functions.
Is there a reason to have that epsilon 2 as well as epsilon 1 to the C?
Unfortunately, our proof kind of uses that.
Okay, but it's possible that it could like work for general epsilon 1.
Yes, that's an open question. I'll talk about it in the end. So truly tolerant testing is still open. Like, let's just say epsilon 1 and epsilon 2 are just like added to far away from one another. Then can you get a polynomial time algorithm? We don't know. Yeah, and also the constant that we get is ridiculously high, because you kind of have to use the polynomial Friedmann-Russell theorem that has this huge constants and stuff like that. So like, yeah, so I think, I'm not sure if our proof is the right one even to get like the purely perfect tolerant testing algorithm, but this is something that we can just get with our techniques. Right, so let me talk about the proof techniques. Hopefully I can get through it in the next 10-15 minutes. So the first thing that we kind of looked at was like, okay, let's look at something called the Gowers norm. That's going to be like the metric estimator that that's going to be the tolerant version of it. And so Gowers norm is very well known in classical TCS, and people have looked at it a lot, but in quantum, not so much. And so the first thing that we did is, let's just look at Gowers norm and see what's really going on there. So let me define what the Gowers norm is. It's just a function that it's just this quantity that has this ugly looking expression, but maybe you don't need to look at it too much. Let's just look at some examples and see what's really going on under the hood. So, in some sense, if we just take k equals to 1, then this expression on the right is just f of x plus h. So it's kind of just taking the derivative of f in the direction h evaluated on x. So the Gowers 2 norm is just kind of taking the average derivative of a function evaluated in an average direction and an average point. So if you look at k equals to 2, this is x plus h1, x plus h2, x plus h1 plus h2. Again, kind of this is like the derivative of h1 in the direction x, h2 in the direction h1, and you can write this as a second order derivative. So this just kind of tells you like the Gowers norm is kind of taking an average derivative of the direction of your choice.
Shouldn't this be product of that?
Yeah, so the point is,
When your f is Boolean.
if it's -1, it's a product, right? 0, 1.
So you write -1 to the.
Oh yeah. That's the way I'm writing it. I'm writing it as -1 to the. Yes, exactly.
Because otherwise you have just linearity of expectation.
Right. So technically, it should be a product of -1 to the Boolean function, and I'm just writing it. So it should be -1 to the summation of the exponent. I've just written it this way for succinctness. Yeah, you're right. Actually, when I talk of quantum states, I define it this way already. So, yeah, I just copied this from a paper. So when you look at quantum states, you can define like we know that every quantum state can be described by an L2 norm vector 1, by an L2 vector 1. So the amplitudes are just a long vector of size 2 to the little n, and its L2 norm is 1. We can define its Gowers norm this way. It looks a bit ugly, but it's very inspired by this. And this is just some technicality. I guess the question is like, okay, this is just a straightforward generalization of what we did classically. The question is, what's the use of it? Is there any use of defining this notion? So classically, there's something called the inverse Gowers theorem, which is extremely good. So it says the following. So if the Gowers norm of a function is at least epsilon, so if it's at least epsilon, then f is actually close to a degree 2 function. So this was the seminal work of Srinivasan back in 2007, and then finally he relied on a conjecture that was recently solved by Gowers, Green, Manners, and Terence Tao, which says that if your U3 norm of f is at least epsilon, then f and g agree on a body of epsilon fraction of the inputs. So if the U3 norm is large, then f is close to a quadratic function. And the main result that I'm going to be describing in the next 2 or 3 slides is if the Gowers norm is at least epsilon, then there exists a stabilizer state which is close to my unknown quantum state. So kind of like, as I mentioned already, like this kind of like extends the classical proof, but classically, like Srinivasan didn't have to go through certain things that we have to go through, like because he's just working on functions and we're working with arbitrary quantum states. So there is some non-trivial extension of his proof, and like there are some results in additive combinatorics and stabilizer coverage that we had to do in order to prove this inverse Gowers theorem. But once we have this, then we are completely done. Right, so I'm going to describe the proof of the inverse Gowers theorem for the next couple of slides. But I guess the main thing that you should keep in the back of your mind always is like, we know that every stabilizer state is characterized by a stabilizer group. So if your Gowers norm is large, I'm trying to find some sort of stabilizer group structure in there. The question is, how do I do it? And that's what I'm going to be describing now. So part 1 is defining an approximate group. Like stabilizer sub, it's a group. First, let's find a group first before I talk of stabilizer subgroup. So psi is an unknown quantum state. This is just a Pauli, and this is just my expectation, right? So think of this as the Fourier coefficients or like the p psi's that I described in the start of my talk. So what does high Gowers norm mean? So the first thing that we show is if the Gowers norm of a state is large, then if you just look at this function, it has some structure in it. If I pick an x comma alpha and a y comma beta, then x plus y and alpha plus beta also lies in there with some reasonably good probability. So these p's are not arbitrary, but they kind of have some structure. If you want to get more intuition, if psi was exactly a stabilizer state, then for 2 to the n many things this is 1, for 2 to the n many things this is 1, and this is 1 just because it's a group, so it's 2 to the 2n on the left hand side, and this inequality is true, but what we show is if the Gowers norm is at least gamma, this is still approximately true. Like when gamma is 1, this is exactly true, and gamma is anything, this is like 1 over square root of n, this is still approximately true.
So what is Wx alpha?
That's just a Pauli, like you can describe every 2n.
So x is n
bits and alpha.
alpha.
Exactly,
Oh,
yes. Sorry. So x and alpha are 2 n bit strings. 2 n bit strings, x is n bits, alpha is n bits. So large Gowers norm implies some sort of structure is happening inside this piece. And the question is, okay, Can we go somewhere further with this? So the first thing that we do is let's just consider the set S, which is a set of all P of X from alpha is greater than gamma. So recall that if again psi was a stabilizer state, this quantity would be exactly 1 for all the stabilizers of the stabilizer state and 0 otherwise. So we know that this, so let's look at all the things which are at least gamma. It's not 1, but it's at least gamma. Can we try to get some structure out of this? Yeah, like I said, if psi was a stabilizer, P of X comma alpha would have been 1, but let's just look at the large Fourier coefficients or the large Pauli masses. So the first thing that we do is we look at S, and we're going to construct probabilistically a set S1, which just kind of picks elements in S this way. I'm not going to go into this probabilistic construction, but we're going to pick an S1 which is a subset of S, only some certain interesting coefficients. And I'm going to define this event, L of Z. So think of Z as a subset. If I pick an X comma alpha and Z and a Y comma beta and Z, what is the probability that X plus Y and alpha plus beta lie in Z? So kind of, again, like the inspiration for this is again this quantity, like if X plus alpha is in Z, Y plus beta is in Z, X plus Y and alpha plus beta is also in Z. So kind of like L of Z quantifies how close is Z to being a group. And the main technical lemma that we show is if this we show that this quantity is at least, if we probabilistically pick S1 this way, then the expected value of L of S1 is greater than gamma. In particular, that implies that S1 is approximately a subgroup. So that's all I've done in this slide. All I've said is, okay, I had this interesting set S of high weight Fourier coefficients or high weight Pauli expectation values. There exists an S1 inside there, which is approximately a group. When I mean by approximately a group, if I pick an X comma alpha and S1, Y comma beta and S1, with good probability, X plus Y and alpha plus beta lie in S1. Where by good, I mean Pauli. Recall, the goal is always to find a stabilizer subgroup. We're kind of getting there. We just, with no structure in S, we found an approximate subgroup. Can we first find an exact group? So there's this, there's this recipe that people like Sarmanitsky did, and it's very well known. That's called finding sets with small doubling constants. If you're approximately subgroup, then there's this theorem of Balog, Samaridi, and Gowers that say like there exists a set within S1, which is S2, which is still which has small doubling. What I mean by doubling, if I look at S2 and if I add S2 with itself, that is, take every element of A plus B, where A and B is in S2, the size of this set is small. So if S2 was a group itself, S2 plus S2 is equal to S2, so this would be a constant 1. But if it's approximately a subgroup, the BHD theorem says that this quantity is still nice. Then you can use this result of Gowers, Green, Manners, and Tau, where they show that if this condition, if S2 had small doubling constant, S2 can be written as a union of cosets of a subgroup V. I think I'm a little bit running out of time, but so then we use the GGMT, and I guess maybe the thing I'm going to get at is you have S2, it is covered by cosets of a subgroup V, and using some sort of calculations, one can show that if you look at this function X, this P function, which is just a characteristic distribution of my unknown quantum state, inside the subgroup V, this weight is actually pretty large. So I first found an approximate subgroup. Now I found an exact subgroup whose weight is large. I have an unknown quantum state, and I found an exact subgroup using this 1, 2, 3, and the weight inside the subgroup is actually pretty large. Again, we have found a subgroup, we have not found a stabilizer group. So a subgroup is defined by inner products, but a stabilizer group is defined by the symplectic inner product. So we're still not done yet. And that's what the final part of the thing will be. So we found a subgroup, V, whose weight is large. Then we find a stabilizer subgroup. And the idea is again to go back to some version of GGMT. Instead of covering my S2 with subgroups, I'm going to cover my groups with stabilizer groups now. So let's just say I could cover my unknown group with just a union of stabilizer subgroups, I'll be done. Let's just say I can cover it as a union of k many stabilizer groups, I would have this relation. And using some well-known techniques, this also means that I've found a stabilizer state whose inner product is at least Pauli of gamma, the unknown quantum state. But the question is, what is K? Like, how can I cover an arbitrary subgroup with just a union of stabilizer subgroups? So there are two ways we went about this. The way we spend a lot of time thinking about it is this conjecture and additive combinatorics. There's a combinatorial way. Let me tell you this additive combinatorics conjecture. Like, we asked the authors of GGMT, they said this was stronger than PFR but weaker than Bogoliubov. But I don't know what the statement, like, I don't know what how to prove it. So think of S as just a subset of 2 n-bit strings. Think of NAC as a set of maximally anti-commuting sets in S. That is, there exists Z1 to Zt such that the symplectic inner product is exactly 1. And the conjecture that we have is if S has small doubling, that is 2S is at most m times size of S, then the NAC of 2S is also small. We tried this for several sets and we tried coding it up and things like that. It seems true. We don't know how to prove it. Yeah. So this is a conjecture, and if it were true, that would imply K is small and we'd be done. So this is where we were stuck, and we posted a paper online, but then eventually I think we realized that we were just going about it the wrong way. There's a totally quantum way to do everything. Like you don't need this mathematical conjecture. We are able to show now that if this quantity is large, like what I started in my slide, then you can actually show that K is poly of 1 over gamma. That the stabilizer covering of an unknown subgroup is also poly of 1 over gamma. And if you just put everything together, you get that if the Gauss number is large, this inner product is at least poly of 1 over gamma. I went through this a bit quick, but maybe let me just give you a quick recap this way. So we start with the set S, which has all high weight expectation values. If it was a stabilizer state, this quantity was exactly 1 for the stabilizer subgroup. But I'm just looking at all x's for which this quantity is at least gamma of 4. Then, using our main structural theorem, what we show is there exists a choice set, which is approximately a subgroup. So if I pick x and y in a S, x plus y is also an S with high probability. Then, using PSG, we get S prime, which is a subset of S, which has small doubling constant. And then if you use polynomial Freeman roots and some claims that we have, you can show that the weight inside my subgroup is large. And then when the weight in the subgroup is large, we know that it can be covered with stabilizer subgroups. So we start with large Gauss norm. We show that there exists a stabilizer state, which is close to my unknown quantum state. And at this point, I think the tolerant testing algorithm is pretty simple. Just take copies of the state, estimate the Gauss norm. Using the no instance, you have this inverse Gauss norm. In the yes instance, we use a previous result of G and W that says that Gauss norm is at least epsilon 1 to the 6. And this is where you get the 6 factor, but yeah, I'm not sure what to do about that. And if you just pick the tolerance of your estimator to be like the difference between poly of epsilon 2 and poly of epsilon 1, you get a distinguisher for this. And estimating the Gauss norm on a quantum computer just requires like n many gates. It's pretty simple. Yeah, I think that's it. We saw how to learn stabilizer states. We saw how to test stabilizer states. Like what Kevin was asking, like, can we get a tolerant tester with just complexity 1 over epsilon 1 minus epsilon 2 without needing this assumption in epsilon 2 that's open? Can we tolerant test richer class of quantum states? I think ours is the first work that even gives a tolerant tester for any class of quantum states. Like, I think finding more examples would be nice. Yeah, for the next part of the talk, I'm just going to be talking a simpler class of quantum states called phase states and understanding whether we can test them. And that's it.